Okay, welcome everybody again to day 2 of Biology of Fishes. It's Thursday, the 30th of August. We got our complement of folks in the live sessions here today. We've gone around the room and I've met them and got their names. I've got a couple of people who have sent me images and in one case recorded audio, in the other case just some text, and I would welcome additional ones, and I'll give you an example of how these work next time. We'll play them into the record. So I'm going to skip that today. I didn't get them in time to do that. I think I've heard from nearly everyone now. I've been talking to some of you on the phone, particularly distant people. I've gotten a response to my greetings message, except for, I think, for one person. And I always worry when I don't hear from people that, they're not hearing from me, and that's why. Now, sometimes I know they're just busy. I appreciate that. But I do need to know, that you're out there. In other words, I need proof of life or proof of involvement, engagement. And it's really important, particularly for folks that I'm not going to see in the classroom, because I'm anxious to establish a connection with you individually. And I hope you'll work with me on that. I guess I ought to say, I'm thinking about that old adage, nothing ventured, nothing gained. You got to lay something on the line. And if you'll just try to meet me partway, halfway, you're going to gain a lot more than you venture in the deal. But you got to lay it out there first. Even you don't win the lotto without even that $1 bet. Of course, you may not win the lotto anyhow, but this is a lot better deal than the lotto, I think. I'm going to make an effort from now on to start my emails with the subject line WFSC417617 : and then whatever the specific subject is, because I think there's a tendency in this day and age, particularly with cell phones and small displays, to just glance over those subject lines and only pay attention when you think there's a reason. And I've even had people come and tell me that their tmu.edu emails are going into trash. That's probably not good. You might have an official message that you really need to see. So you might want to check and make sure that if you've got some .tmu.edu emails, that they're not going to junk. So I'm going to try to make sure that you've got no reason to ignore my emails. I'll always try to give you a substantive subject line. I guess almost worse than a wrong subject is no subject, and I always try to avoid doing that. Sometimes I slip up. But I encourage you to, in all of your communications with folks, just good policy, I think, to give them a substantive subject line, and don't recycle the subject line too many times, the re, and it's the same old subject, but it's totally changed by that point. And the risk there is that somebody will see the re and think it's a message they've already responded to, when in fact it's a new idea that they really needed to know, and you needed them to know it. If the goal is to have people communicate with you, and you with them, then you really ought to work at it to make sure it happens. And I try to. You'll notice that I'm about as responsive as anybody you deal with, certainly anybody on the faculty. When you send me something, you get something back, pretty quick, within a day or usually, within maybe a few minutes or a few hours. And that's by design. I want you to know that I'm on it. I want you to know that this is the most important thing I'm doing right now. And that's one way to assure that. I'm going to repeat some things I've said before. Be sure and do that Getting Started Flash playback. It'll tell you how to do stuff, how things are going to work. Watch the OrphanView promo. Shows you why OrphanView is such a good deal in Windows XP, and I wish it were a good deal in Windows 7, and Ray's working on it. We got people in our IT group trying to find another player that will allow this speeded up playback in Windows 7. with good style and good quality, but we haven't located one yet. There's some other files right up there at the front that I call your attention to. One of those is this Functional Relationships PDF. And with Internet Explorer, typically you can just click and open PDFs without, saving to your hard drive or without doing anything else. And this is just an old scan of a, hand-produced, drawn and typed file. And what it does is lay out a series of functional relationships that are useful in everything, but in this course as well as a lot of other courses. Starting with the simplest idea of y is independent of x, that's a constant, and then you got linear equations and polynomials, which the linear is just the first order of polynomial. And then go into more complicated equations with some notes about why they're important in biology of fishes. For example, the power function often is used to express the relationship between animal weight and length, or height. In the case of fish, length. And you don't have to memorize these things. These things are a resource. They're a reference. I wouldn't have done it except I couldn't find any place where it was all pulled together in a simple, easy-to-use form. So you might want to just print that thing off and have it handy as you listen to me or as you do your labs, because all these functions, particularly that one there, the exponential, is going to come up. Now, thanks to Robert Vega's suggestion, didn't mean to get out of that, I meant to go back. I developed a Excel equivalent. It's in Excel 2003 that allows you to actually go in and explore these functions. I'm not going to take the time to open that thing up, but each page, each sheet of the Excel file is one of those functions, and you can go in and you can change the parameters, and you can see the graph and see how the thing responds when you change the parameters. So that'll be very helpful, not just here, but somewhere in your future, I bet. If you ever deal with any math at all, most of us do sooner or later. I mentioned that sample exam. I think that's a doc file. You might want to look at that. And then here are the records. There's the one that's already up there from Tuesday. And every time we do a session, it'll be added on the end. Here's the PowerPoint black and white version. And that'll probably open. Well, see, that one doesn't open automatically. It opens like this, though. You might notice I corrected the date there. I said spring. I forgot to change that. It wasn't spring. It was actually updated just last week. So it's fall 2012. And then there's one today, and it's already up there. Right there. Enviro PPT. That's the topic we're going to talk about. And I have passed out here in the class both the introductory session PowerPoints that I forgot to pass out last time, as well as the one for today. And what I do is, for the local group, for the live audience, is I print these things out, 3 slides per page with notes, the notes format, and that lets you, as I go along, either live here in the classroom or on the record at a distance, and later in time, it lets you make notes about what I'm saying, things that occur to you, questions that you need to ask, warnings that I said this will probably be on the exam, or whatever. So I encourage you people at a distance to do the same thing, to go ahead and print that off and waste that ink. I do it in black and white instead of the colored format that I use in class, so that it makes it easier on your printer. Then there'll be some other files that we'll introduce as we go along, and we're going to have a look at a Stella file, I think, for the first time today. Get a little introduction to that. Down here is lab, and lab comes along soon, next Tuesday. Local folks will need to come prepared on Tuesday with only their thinking caps, I like to say. Everything else will be provided. Well, actually, there's one other thing that you might want, and that is a USB. It doesn't need to be a big one drive, a little flash drive with a couple of gigs on it. Everybody's got 3 or 4 of these in their pocket at this point. And that's so that you can save the work that you do in the local lab and take it away safely instead of risking it. You know, I've had people store it on the computer and somebody else wiped it, or I've had people send themselves an email that never got there, you know, with an attachment. Maybe the file was too big at some point. So be careful about that, and, you know, save your work and save it frequently. And the way to do that's on a USB. There's going to be a lab expectations and grading. It's not there now because that's the old one. Ashley and Donovan are working together to produce their expectations for this local group. I mean, for this current group of both local and distant folks. Remember I said Donovan's going to handle 417, both local and distant. And Ashley's going to handle 617, both local and distant. That way, any differences in their standards or whatever will have, you know, won't differentially affect people within a class. Yeah, I had a question, Sean. No? Okay. So anyhow, they'll do this before next Tuesday. They're working on it. I think the rest of the stuff having to do with lab we can work on when we get to it. Trying to think if there was something else that I wanted to nag you about today. I guess the main thing I need to nag you about is don't get behind. Stay with me. Keep up. You know, it'll be good if you stay with me. If you get behind, it'll be terrible. And the further behind you get, the more terrible it gets. So don't do it. Okay. Let's leave the internet, and I'm going to close that and not go back, because I've learned the hard way that if you've got a connection to a browser, whether you're active or not, it takes up file space. I can't figure that out. Ray and I were talking about that after class last time, but you know, it inflates the file size to have Internet Explorer or Chrome or anything else open like that, even email. So I try to make sure I don't have it open unless I need it. What I need today with you is this file. You know, we're sort of setting the stage here. We're going to talk about fish biology, but in order to talk about the biology of fishes, we need to we need to sketch the theater, the stage on which they operate. And that's what this is about, you know. And I'm going to be talking mainly about physical chemical environment, because I think that dominates things like substrate and topography, and you know, people that deal with terrestrial wildlife are more focused on properties of habitat that are organic, that are living, or soils, vegetation. You know, we're going to talk more about the chemistry of water and the physics. So I've already done a promo on the functional relationships PDF, and so I would encourage you to go to the archive, download the PDF at least, and I would think you undoubtedly will want to look at the Excel file. You want to have a copy of that to take away with you. We may keep adding to it. You know, I'm working on it as we go along. So let me begin by pointing you to the reference, the course text that is recommended but not required. It's that second edition of Carl Bond's book. Very good book. Chapter 29 is the one that deals with the topic that I'm going to talk about today. And I'd like to begin by talking about some of the special things that make water a whole different world for the aquatic organism than the air is for us. You know, our medium is essentially air. You know, we stand on the ground, but we breathe the air, we feel the air. And fish swim in the water, so the water is a different place. There's a set of interesting connections among depth, density, viscosity, and pressure in the aquatic medium. First of all, something about the range of values And in regards to depth, the depths that fishes occupy range from a centimeter or so in ephemeral rain pools in the tropics. Here today, gone tomorrow, here again the next day, to, the deepest oceans. And the deepest ocean is in the Marianas Trench in the western Pacific, around 11,000 meters, about 7 miles. Fish live at all those depths as far as we know, But by far the bulk of both species and biomass are much closer to the surface, within a few hundred meters. The mean depth of the world's oceans, by the way, is about 4 kilometers, 4,000 meters. Water, pure water, has a density of 1 gram per cubic centimeter when it's under standard conditions of temperature and pressure, 1 atmosphere, and whatever that magic temperature is that I can never remember. It's around 14 or 15 degrees, I think. For our purposes, it's 1 gram per cubic centimeter, independent of anything else. Notice that I've written, and I lost that cursor there because I forgot to do my Control A. Notice that I've written the 1 gram per cubic centimeter carefully there. I want to be sure that we understand that it's 1 gram in a cubic centimeter. That's a little cube, a centimeter on the side of water. Sometimes you will see that written, more normally you'll see it written 1 gram dot, a dot product, 1 gram dot cm minus 3 in the numerator. That's another way to do it. Sometimes you'll see people carelessly write 1 gram / centimeter cubed, and you're not sure whether you're cubing. Well, in this case, I guess it wouldn't matter, but in a lot of cases it would. You need to be careful keeping your dimensions organized properly so that there's no misunderstanding. Excel will misunderstand intentionally if you let it, seems like. So be careful. 1 gram per cubic centimeter, and the contrast with what happens in air is pretty dramatic. That's 775 times the density of dry air under those same temperature pressure conditions. And if you raise the temperature a little bit, to about 20 degrees centigrade, the contrast is even more. I think it's close to 1,000, 800 and something. 890, I believe, at 20 degrees. So water is a whole lot more dense medium. It's more viscous too. That is, it's more syrupy. It resists motion through it to a much greater degree than moving through the air at the same speed. So it's really a lot of work to go through the water fast, and takes a lot of energy. And the people who build nuclear submarines and study tuna swimming know this very well. Water is 100 times as viscous as dry air at 0. And even at 20, it's 55 times more viscous. Pressure. Water's a liquid. Air is a gas, a mixture of gases. And so liquids are relatively incompressible, we say. And that means that, before I get to that, I guess there's a note here, and then I will look at the first graph in biology of fishes. I had a student one time who said this shouldn't be biology of fishes, it should be graphology. This shouldn't be WFSC4117, it should be graphology 417. But anyhow, Susan she had a point, and I thought about it many times over the years. Boyle's law says that the volume occupied by an ideal gas is inversely proportional to the pressure exerted on that gas. And so that's why gases tend to get bigger, or volumes tend to contract or expand of gases depending on the pressure. And so as you go down beneath the surface of the water, out of the terrestrial world and into the aquatic world, the relationship changes in terms of its linearity, and the scale changes drastically. So notice that at sea level here, there's a break between, an inch or so there on your monitor. There's going to be 5,000 meters in the air, and that same inch or so is going to be only 10 meters in the water. So I've made a dramatic change there at sea level. And notice that the relationship as you go down in the water, at least if you don't go too far down, is pretty linear. It's about, and this is one of my rules of thumb that I would encourage you to take home, and store away in memory, so that when you stand in front of a group of folks in the U.S. Fish and Wildlife Service or USGS or Texas Parks and Wildlife, and they ask you these questions to see how, what you know this. It's 1 atmosphere per 10 meters as you go down in the water. That is, the pressure exerted on fish and everything else as they go down in the water column is 1 atmosphere per 10 meters. And so if you're down there at 3 meters, if you're down there at 20 meters, you got 1 atmosphere of air bearing down on the surface of the water, and then you got 2 more atmospheres of water bearing down on you. So it's 3 total at 20 meters. And as you go up in the air, the pressure goes down, and you got to go all the way out to intergalactic space for it to go to 0. So obviously this can't be linear, because when you get to about 10,000 meters, we're talking about a quarter of an atmosphere. So the weight of all the air from there out to intergalactic space pressing down, the acceleration of the mass under the force of gravity, that's what we call weight, the force, is about a quarter of an atmosphere. And as you go to 5,000 meters, it's a half an atmosphere. And then as you go all the way down to the surface, it's 1 atmosphere by definition under standard conditions. Of course, in the middle of Isaac, or even worse, one of the others, I guess Katrina, that's not an atmosphere anymore. It's like 0.8 even, or something really serious. I mean, that'd be a real low pressure, right? But normally 1 atmosphere at the Earth's surface. So 1 atmosphere is all the air there is from the surface out to intergalactic space, the weight it exerts at the Earth's surface. Water has a lot more density and therefore a lot more weight, and it only takes about 33 feet of water to be 1 atmosphere. That's about 10 meters. That's why 10 meters. It takes 760 millimeters of mercury, or 76 centimeters, 3/4 of a meter of mercury, to weigh as much as all the atmosphere from the Earth's surface out to intergalactic space. So that's why we say that 1 atmosphere is 760 millimeters of mercury. And then there are other measures too, bars and so forth, that are thousands of atmospheres basically. And I think that's what's normally reported in Weather Service documentation. So, a little test here of your analytical reasoning ability. And I usually foul it up, but I reviewed it, so maybe I'll remember it this time. How much pressure is on a fish living at the bottom of the Marianas Trench? You have to think about, how deep is that? Well, it's 11,000 meters. And if it were linear, and it isn't really, I wouldn't bet on that, but if it were linear, how much would it be? Well, it'd be 11,000 meters, 10 meters per atmosphere, that's 1,100 atmospheres and 1, because you got the air above it. So it's 1,101 atmospheres linearly, but I wouldn't bet on that. Allison's going to tell us exactly. She knows how much it is. Do you know? I don't know. You look like you knew. I don't know. Zoe knows, though. Yeah. I don't know how many atmospheres really, but I can tell you it's a lot. I can tell you it would crush you like a whatever. But fortunately, water's pretty incompressible, and so things that are made out of mostly water and hard parts, solids, are not too compressed. But it explains why, at the bottom of the Marianas Trench, you're not going to find many fish with air or gases of any type in a swim bladder. So swim bladders get to be pretty rare once you go below about 1,000 meters, actually. as you'll find out later on. We'll talk a lot about swim bladders and buoyancy and the dynamics of regulating density, in effect, overall density, because the overall density of a fish is the density of its hard and liquid tissues plus its gas, and it uses gases to offset the heavier than water density of its other parts, so it can be neutrally buoyant. And since it can't do much about its other parts, what it does is adjust the gas. Pretty neat trick. Something we don't have to worry much about. Solids. Water is said to be the universal solvent. It really isn't, but it does dissolve a lot of stuff. And the thing that really makes the marine environment different from the freshwater environment, aside from the much greater volume and depth, is the fact there's a lot more stuff dissolved in marine water. About 200 times more stuff, more dissolved solids, that's DS. And sometimes you'll see TDS, that means total dissolved solids. And I use the FW to mean freshwater and SW to mean seawater. I don't use SW to mean salt water because there's all kinds of salty water in addition to seawater. Some people use haline to mean seawater as opposed to saline. I don't really use those words too often. A lot's been made, a very lot has been made of the similarity in the kinds of salts and the distribution, actually, the proportions of salts in the sea versus in the plasma or the serum of animals. They're similar. We'll spend a lot of time talking about one of your topics, favorite topics, osmoregulation, and how fish manage salt and water in their blood tissues. But for now, I want to focus on the environment, and I want to say that the normal ocean, here I say 34 to 35 parts per thousand salt, and some people would run that down a little bit and cover coastal waters that are more like 32, or high Arctic waters, which tend to be a little lower. But I think 34 to 35 is a good number for most of us. Another thing on dimensions, PPT, parts per thousand. And I say that's about the same as grams per liter. And that's because, there's a gram of water there's 1,000 grams of water in 1 liter. So 1 part per thousand. So what we're saying is 34 to 35 grams of salt in a liter of solution is the typical total dissolved solids concentration in normal seawater. Most of that is ionized sodium chloride, table salt. I guess if you look, it's about 85%, something like that. And the rest is sulfate, magnesium, calcium, and potassium, mainly. Some of you may be thinking, wait a minute, NaCl, 1 Na, 1 Cl, why 30.6 sodium and 55 chloride? Well, it's got to do with the difference in the masses of those two ions. And in fact, I'm trying to remember here, Ray's going to help me, I think it's about lower 20s, 23 maybe is the atomic weight, the molecular weight, the atomic weight of sodium. And I think chloride is the mid-30s, somewhere 34, 35. And that's about the same ratio as the 30 to the 55. You could check me on that. I mean, there's some sodium and some chloride that aren't necessarily associated with each other, so there may be some imbalance. I mean, there are things like potassium chloride and sodium sulfate. But I think that's about the normal proportions. That's the normal proportions in seawater. But there's a lot of salty water that isn't seawater. And the further you get from the ocean, the stranger it gets. And out in West Texas, we got pretty salty water in a lot of places. that the local folks out there call alky, because it's not really sodium chloride salty, it's pretty much magnesium sulfate salty. That is, the dominant ions out there are magnesium and sulfate. And, the old Permian Sea, which is still there, by the way. If you don't believe me, drive out west of Odessa on Interstate 20 and take a look at a little place called Penwell. You look out onto the old Permian Sea. It's solid ground now, but there's still oil wells sticking up. Looks like the Gulf. Periodically and in places, that Permian Sea emerges, and you actually can see it on the surface in places like gravel pits and the Pecos River. And when you test that water, you may find out that it's got more total dissolved solids than seawater. Knew a gravel pit and knew it pretty well out around Royalty, which is down in the Pecos Basin, between Pecos and Fort Stockton, and that thing had about 40 parts per thousand total dissolved solids. And it was pretty much magnesium chloride. It was precipitating out stuff, and I still got some of the chunks of stuff up in my office. I don't know what they are. They look like, coralline deposits of some sort. But it's not sodium chloride. And, what happens is, as water, ancient seawater, dissolves the minerals and is reprecipitated, and all kinds of strange dynamics go on, it changes its distribution of salts pretty drastically. And surprisingly, marine animals can cope with it to some extent. We've actually experimentally grown things like red drum and Penaeid shrimp in some of that water. And here's the I guess the surprise or the good news or the strange thing. If you adjust the total dissolved solids in some of that water out there in the Permian Basin to about 10 parts per thousand, which is optimum, it turns out, for juvenile marine things like red drum, they actually can grow better than in 10 part per thousand seawater. But it seems like it's a delicate balance. In other words, if you look wrong, if you look at them wrong, they die. But they can actually, under optimum conditions, good aeration and everything. I think what happens is, if you mess up, since that dominant negative is sulfate, boy, it goes to sulfide, and then you've got a lethal environment. Hydrogen sulfide isn't. In fact, I almost lost a student out there one time, Ray. He was stomping around in one of the overflow areas from a windmill pond, and there was so much hydrogen sulfide that he started stirring that stuff up. It just about knocked him out. Gave him a bad headache. But red drum and shrimp, as long as it doesn't go anoxic. Of course, if it goes anoxic, all bets are off anyhow, right? But just a short period of anoxia under those conditions could be lethal. I mean, fish can hold their breath for a while, but, well, so to speak, hold their breath. They can live at low oxygen, survive. Well, it's just an aside there. I'm off and off on the sides, and you have to bring me back. Students usually don't want me to come back to the main line. They like these little asides. So there's seawater's minor ions, I call them, as far as the proportion they constitute of the total dissolved solids. And sulfate, you can see, is 7.7 in seawater. It's a lot more than that, maybe, out in the Pecos Basin. Calcium and strontium together are listed together because when these data were generated, it was hard to differentiate the two. They're close to each other on the periodic chart, and they don't really separate very well. Maybe you could do it with modern ion spectrophotometry methods, flame nowadays, but back then it was hard. So sulfate, magnesium, calcium, and strontium together, and potassium. Some variation. Lots of variation. Polar seas tend to be fresher than the world average. They've not got as much salt per unit volume. Usually, if you go out in the Beaufort off the north coast of Alaska, the salinities regularly are running around 31 parts per thousand. And don't tell me now that it's because there's lots and lots of freshwater inflow, or there is tremendous, that the ice has frozen all the salt up, locked it. That works the opposite. Ice actually excludes salt when it freezes. So that you can actually melt icebergs, and even if they're formed in the sea, you can get some fresher water out of them. But it's because the precipitation to evaporation ratio is so much higher. Not that it rains a lot, it just doesn't evaporate very much at all. So over time, if you've got it sort of contained and not allowed to mix with the rest of the world ocean, you get a lower salinity because there's a lot more precipitation. A lot of it's in the form of snow. Then there is evaporation. You go to the inland low latitudes, desert areas like in the Red Sea or our own Laguna Madre off the coast of Texas and Mexico, salinities can be way above the normal ocean because there the evaporation exceeds the precipitation and freshwater inflow that's related to precipitation. I mean, there's not a lot of freshwater inflow under normal conditions to the Laguna Madre. And Laguna Madre, Baffin Bay, down off the coast of Texas, south of Corpus, can be 90 parts per thousand. And believe it or not, the world's record, I may be stepping too far out there, spotted sea trout come from those kind of habitats. They don't mind. They may mind, but they outdo their siblings in other places. Anyhow, trophy spotted sea trout are caught in Baffin Bay, despite the fact that Baffin Bay is a hypersaline lagoon, big time. There tends to be a gradient of salinity along the coast of Texas as along the coasts of many other parts of the world. In the case of Texas, fresher water, the further northeast you go, the more toward Louisiana, and saltier water, the more down toward Mexico. Sabine Lake, up near the boundary between Texas and Louisiana, can be almost fresh a lot of the time. Probably it is now, given the fact that Isaac has probably freshened it up some. And as I already indicated, the Laguna Madre down in the south can be really saline, really haline. And, I'm at the point where I think I'm going to introduce you to your first Stella model, which is a good one. You're going to like this. It doesn't have anything to do with fish. It has everything to do with salt. And it demonstrates the points that I was just making. And let me see if I can get out of this. I think what I'm going to do, and most likely we're not going to have time to do much else, so I'm just going to end the show here. And go back to our web page, our archive, and do what you want to do. And I'm doing it on the record so you can watch me do it. So what I need to do is go down to that part of the record. There's SAL STM. The STM indicates that it's a Stella model file. That's the suffix, the 3-character suffix on the file name. And by the way, be sure and watch the Getting Started video and pay particular attention to the part about file endings and how they're hidden from you by default. When you take Microsoft Windows out of the box, you don't get to see the file names. If they're file names of known type are hidden, and you want to go in, and I showed you how, you want to go in and fix that so that you can see the file names. Why in the world wouldn't you not want to see something important? And where you really find out about how important it is when you try to do, well, first of all, if you do a double click, you don't get anything much that you can use. So you find that out. And please don't call me up and say, Dr. Neal, my computer's not working. I'm getting hieroglyphics when I click on the Stella model. No, you're always going to get that. So what you got to do in the case of these STMs is do a right click and save file or save target or whatever it is, depending on your browser, it's going to be a different label. Save link. Save target as. And I'm going to put it on my desktop. And notice what it's saying down there. It's saying that that's an HTML file. Got something to do with security, and Internet Explorer and Windows have gotten together and they've decided that anything with an STM ending is probably going to be a virus. Well, I guarantee you that one's not going to be. So what you have to do is you have to play some games, and that is with Internet Explorer. You don't have to play this game with Chrome. Chrome is smart enough to know better. But with Internet Explorer, you got to go in and change the file ending, file name, to STM. You can do this after you've moved the file if you want to, and then it'll come up and say, hey, you can't use this if you change the file ending. Yes, you can. In fact, you can if you don't. But I like to change it at this stage, and then you got to go down here and change this from HTML document to all files. So you got to do that. It's real important because you're going to be doing it, whether you like this file or not. You're going to be doing it for Ecofish. It's the same way. So we're going to save that as sal.stm to my desktop here. It's not a real big file, so it saves pretty quick. And then we're going to open it with Stella. I think my default on this computer for Stella is Stella 7R, which stands for research, and that's the same version of Stella that's on the computers here in the room. But we got a problem with Stella that I'll talk about more next week when we deal with lab, and that is that there's a whole bunch of different versions, and I've only got, I think, 4 of them on this computer. The last one doesn't have this familiar look that these 3 have. It is here, Stella 9.1.3, I think it maybe is Stella 9.1.4 now. And if you go to the Stella, the IC Systems website that I pointed you to in my greetings message and in my getting started video, and download the demo, that's the one you're going to get. And those of you who are not able to work here in the lab are going to get copies, one way or the other, of this program, and that's the one you're going to get. But in the room, the computers here have Stella 7. And I think I'm going to try to work it so that all of you can use, if not the full function Stella 7, at least a demo that allows you to do everything but save. We're going to work on that. Okay, what I'm going to do, though, is open it in Stella 7. And to be sure that's the version, I'm going to go ahead and open Stella 7. And then the next time I open something, I'll open it in 9 so you can see how it looks. So the one way to be sure that, the default program is going to be that you're going to get what you want instead of the default is to open the program first and then open the file inside that program rather than the other way around. I think on this machine it would have come up 7 anyhow, but okay, so there's Stella 7. That's the way it's going to look. That's the way yours is going to look here in the room. And it's going to have this little globe here, and that's the conceptual layer. And then when you click on that in Stella 7 or 6 or 8, you get this little chi-square.
So you can't see the globe.
You can't see. Why couldn't you see the globe? I guess because this is off the screen.
Right.
Sorry, folks. Here in the room, you won't be able to see it. You'll be able to see it on the playback, though. I got it here on my computer. So anyhow, I don't know what we can do about that, Ray, short of getting up there and messing with the projector. I'm reluctant to do that at this point. That's not too critical. Over on the left-hand side of the screen here, I've got a little globe and I've got a little chi-square. And what I'm seeing now is a little chi-square. And so when I file and open, it's open what? Well, not that. We probably don't want that yet. Desktop sal.stm. That's a version 6 model. That's where I created it. All these models, Ecofish is all in 6. That's because I like to use the lowest common denominator. Anybody with Stella 6, 7, 8, 9 can open 6, but if you've got Stella 9, you can't open. If you've got Stella 6, you can't open 9. So it helps to start at the low end. It's going to translate as an untitled. I don't care. So there's a Stella model. Actually, it's one Stella model quadruplicated, 4 multiplied by 4. Here's one, and then there's another, and if you scroll down, you can see the other 2. And they're the same model except for 4 different bays in Texas, starting with Sabine Lake in the north and ending down there at the bottom. Salinity 4 is Laguna Madre. And in Stella, in the earlier versions of Stella before 9, the plus and the minus let you zoom in and out. So you can back out and see more when you click there. You can see the whole thing now, as well as some text down here at the bottom that explains things. But it's hard to now read the print, right? So you're always playing this game between being able to see the whole picture and seeing the details well enough to be able to tell what you're seeing. So I'm going to zoom back or zoom in again to the point where we can read the stuff. And let me explain the basic idea. This is a good way to start because it kind of gives you the basic idea of simulation modeling. That is, what we're interested in is what's called the state of the system. And in this case, the state of the system is a variable that is salinity, total dissolved solids. And the state of a system is influenced by transfers in and out of the system. So flows in are indicated by arrows in, and flows out by arrows out. In this case, what we're going to be doing is putting salt into the system and taking salt out of the system. And it's actually salt per liter, but we're not going to worry too much about we can multiply by the volume later on in the bay if we want to. So the whole point of this model is to simulate what happens to salinity at a representative point in Sabine Lake as a function of things, a function of the rate at which salt is going in, and as a rate at which salt is going out. Salt is coming in from fresh water, not a whole lot. Not in the case of Sabine Lake. 0.1 parts per thousand is I'm saying the salinity of the average drop of water that enters Sabine Lake from the land runoff. As we look at Laguna Madre, we'll see it's up to 2 or 3 even. The Brazos River right out here west of town is about 1 most of the time. Our drinking water, folks, is about 1, which I'm not sure is a good thing, Ray. But so anyhow, Jacob's Well does a lot of business. I guess some of the other companies do too. Jacob's Well is the local company that does reverse osmosis purification of water. So there's the salinity of the fresh water going in, the rate at which fresh water flows into Sabine Lake, the rate at which salt flows in. Freshwater inflow is basically that's a turnover time, and I'd rather not get too much into the dimensions of this at this point. And then I've got this little variable called rain percent normaling, because I want to play with climate change and dry years and wet years later on. So let's not worry too much about that, except to say that number is specific for Sabine Lake, and precipitation rate, that's specific, that's in terms of actually centimeters a year. 134 centimeters a year is the rainfall rate. And then the evaporation rate is probably way less, 108. What was the precipitation? Well, it's not a way less, but some less. And then we get over and look at some of the others. Let's just scroll down for comparison's sake and look at Laguna Madre. Salinity of the water coming in, 3. Freshwater inflow, not near as much. Precipitation, 68.6. Evaporation, 124. How about the Dead Sea in Israel? That's about 400. 4 meters a year is the net evaporation in the Dead Sea, which explains why it's pretty dead, I guess, and why it's pretty salty. So, then there's another really important thing here having to do with tidal mixing. And that tidal mixing figure has to do with the amount of exchange there is going on all the time on average between the bay and the ocean, the Gulf. And that depends on passes and their distribution and tidal current path. So there's a whole lot more complicated models than this. I mean, the Texas Water Development Board has worked on some really complicated models for modeling the distribution of fresh water in the bays. But, I want you to see how this one works. And without more ado, let me start out by saying the initial conditions here are we've just had a hurricane. Everything is flushed. I mean, all the bays are fresh. There's been so much inflow of fresh water that all that salt's gone. So time zero, initial conditions, everything is zero. And we're going to get 100% of normal rain now, and we're going to start to get normal. And we're going to figure out how long it takes to get normal and where do we get normal at. And the whole idea is that the salinity of the bay represents a balance between the inflow and the outflow of salt. And we could talk about inflow and outflow of water, but it's just easier to track the salt and let the water be there. There's the same amount of water all the time, right, more or less, in the bay. Here's a stellograph, and stellagraphs have this form. The time series graphs do, at least. On X is one variable. In this case, the time of the simulation. And on Y can be up to 5 variables. In this case, we've only got 4 because we only got 4 bays. Salinity is salinity 1, that's Sabine Lake. Salinity 2 is, what was that? San Antonio Bay. Salinity 3 is Corpus Christi Bay. And salinity 4 is Laguna Madre. We're going down the coast. And I'm anticipating a lot of range here, so I got 0 to 60 parts per thousand on my y-axis. And I'm going to simulate for about 3 years, 1,000 days. And the simulation time step, which turns out to be a critical thing in Stella, is 1 day in this case. So every day we're going to update the system, let the salt go in that came in, let the salt go out that went out, and see what the result is. So you got some ideas about what's going to happen here? Probably you already do, right? So let's just try it and see. So we're going to run the model. Now one of the things I like about Stella 7 and 6 and the earlier versions is you can get this little running guy up there. It's like a little run controller, a little, player controller. It's got this, you can hit that button and you don't have to go to run. So, but in Stella 9, that doesn't work quite that way. We're going to do Stella 9 next. Okay, so now I got my run controller. And as soon as I hit this thing, we're going to see the graph. Okay, the graph formed quick. This is a pretty fast computer. That's a pretty simple model. So it didn't take long. We did 1,000 days there in a heartbeat nearly. That's one of the advantages of simulation. So what's the result? Well, the result is that salinity in all the bays went up. It went up faster in some bays than others. In fact, the fastest was Sabine Lake, number 1, even though it reached the lowest asymptote or steady state value, and that's because there's a lot of tidal mixing going on relatively in Sabine Lake. And there's not much in Laguna Madre. It's pretty landlocked. And so the rate of equilibration or the rate of rise towards the steady state is a lot slower. In fact, even after 3 years, we don't really have a complete flat. We call that steady state when the rate at which things are going in is equal to the rate at which things are going out, so you don't get any more change in the thing. That's a steady state. It's not an equilibrium in the sense that there's still stuff going and coming, but it's at equal rates. So you click on Stella, and that's one thing I like about the program is that you can hold down your left mouse button and you can see the values of your variables, both the abscissa or the x-axis, see that's 954 days, and the y-axis shows us the value of salinity in parts per thousand for the 4 different systems. So, what I've got here is a model that conceptually is straightforward. It's the additions and the subtractions, and whatever whatever the sum of those two numbers is what you got. And the only thing that gets to be different between the 4 different versions are what we call parameters, or the characteristic values for a given system. And those are actually from the literature. A guy named David Brock with Texas Water Development Board went out and studied the bays, and there's a lady in Florida who did some studies, and I forget her name. Anyhow, I put all that together, but I just used their numbers and common sense to simulate this. But, I can stand here and tell you that there's a gradient of salinity down the Texas coast, and it's got to do with rainfall, and it's got to do with evaporation. But it's nice to be able to actually nail it down and say, hey, this is what I would expect to happen quantitatively. And then we can play games. We can say, so here we got in a normal year 45 part per thousand steady state in Laguna Madre. What if it quits raining? What if the future continues along the recent past trajectory? What if we get, what if we get 10%? Hate to think of normal. What if we get 10% of normal? Well, it's as easy as just entering, deleting 1 0 and then running the model again. Same scales. Scales didn't change. So even Sabine Lake now is getting pretty salty, right? It's up to about 26 parts per thousand, and probably I'm a little too conservative here. I'm only at 57 on Laguna Madre. I'm surprised it wouldn't be more. But now that's the whole Laguna on average. That's not Baffin Bay necessarily. We'd have to reparameterize for Baffin Bay. Remember, the idea here is that we got a representative point in the system we're trying to simulate for. Well, maybe, we get a break and we get a lot of rain. So maybe notice I'm going in and I'm changing what's called a converter in Stella. That's just this little circle thing. Well, they're used for constants or driving variables. And so instead of we get, 500% of normal. We really get a wet year. It'd be really wet, right? But we can play any game we want. I wouldn't want to try 2,000,000% of normal. That might blow up on us. But so what this says is that if it's that wet, then we're going to get the Laguna and Corpus Christi Bay being about the same, and we're going to get 2 parts per thousand in Sabine Lake. So you can accept the actual numbers or not accept them, but the trends and the ideas are the things that I want you to pay attention to here. And notice what Stella did for us. It allowed us to do some what-if stuff. It didn't cost us a nickel, hardly, except for the software. You get that free. So anyhow, I don't think there's any point in pushing on at this point. I think we'll stop here and come back and pick it up there next time. Don't forget to bring your USB drive, local folks, live folks, to lab. And I will be communicating with all of you, particularly people who are not here today, about Stella. And let's stop. Unless you got a question for me. Be a good time for a question. We got a little bit of time on the clock, and so students at a distance would like proof of life from you guys. Know that there's somebody here besides me. I've got a fancy mic over here. with wireless capabilities, so we could actually hear from you on the record if anybody'd like to say anything.
I was just going to say that...
You just hang on a minute. You don't get to say it without saying it on the record, Allison.
I just want to say that I've seen the Laguna Madre data in the 50s before they did the dredging, and it was at 120 parts per thousand. So.
Yeah. So, wow, 120 parts per thousand. You know what? I suspect that would indicate, maybe even less exchange, so less tidal mixing. Because if you prevent all the passes from working, then you basically turn it into a salt lake or salton sea or Dead Sea. And I would expect that then you're going to see progressive increase in salinity till you get a balance, Also, during the 30s to 50s, we were in one of the driest periods in history, so rainfall rates may have been down in that 10% range. I don't know.
And I think in the 60s, when they started dredging, that helped too.
Yeah. So you can only get so salty. Did you know that? You can only get so salty if you let it all evaporate and keep on evaporating. As long as you got any liquid there, that liquid doesn't get saltier than about, I'm going to say 280 parts per thousand is saturation for sodium chloride. So the Dead Sea is running about 280, 300. After that, the salt precipitates. And you get these big salt structures, So it either goes dry or it doesn't get any saltier than that. But that would probably be a little salty for everything except bacteria, maybe. Yeah.
Is there a point where...
Tell us who you are.
Oh, my name's Lindsay.
Yeah, put it about here and it works better.
Okay.
Otherwise you go boom, boom, boom.
Okay, is there a point where the fish, just tying it back to fish, where they stop being able to have normal processes, or can they adapt to pretty extreme salinity
Yeah, so
levels?
what I heard in that question was what's the maximum salinity?
Mm-hmm.
And we're going to talk a lot about that later on. And I already told you that we got fish swimming around in Baffin at 90, and I guess we had some swimming around at 120.
Yeah, I've got sheep's head minnow up to 150.
150? Sheepshead minnow, that's Saprinodon. That's really a tough salt marsh fish. So I would say that maybe that's an answer to your question, but probably not 280. Probably 150 maybe.
Yeah, they
Be
stop
about the
eating
upper
at that
end.
point.
Oh, okay.
Yeah, they stop eating.
So we'll have a lot more to say about salt and fish and salinities, osmoregulation, that sort of thing. Thank you. This mic, by the way, here that I'm handing around, I call it my karaoke mic. It's a wireless transmitter, and there's a button on the side, and when you punch it once, it turns off to standby, and then punch it again, it's toggle back to green, and that's when people can hear you. And then when you hold it down for a long time, it turns completely off. So there's a mixer here on my cart that mixes my little mic, which I see is now flopping around on my chest. I hope it hasn't been that way for a long time. Anybody notice? Has it been that way a long time? So my voice may not be real good in some of this today. My lapel mic, my little mic here is not positioned the way it should have been, but hopefully it's still picked up. I'll check the record and hope that I don't have to redo it. I've had to redo more than one of these, in a vacuum. I may make Ray come up and listen to the audience now. I wouldn't do that to anybody. All right, we're going to stop. See y'all next time. Thanks.